So now let's look at 8.3 on geometric sequences. So let's first define a geometric sequence. So suppose A sub n is a sequence. And so basically, I mean, it's defined by the function, by the nth term, but basically what you do is you start with a first term, say a1, then to get to the next term you multiply by the same thing. So we're going to say r, and we actually call that, so r is called the common ratio. All right, so to get to a2, it is a1 times r, and I write it in that order because it just looks nicer later. And then to get to a3, the next term, it's the previous term times r, so it's a2 times r. But what is a2? It's a1r times r. And then a4 is a3 times r, but a3 is a1r and then times r. So you can see the pattern here that you have a4, and then this would be a1r raised to the third power. And this was a1 raised to the second, and that was to the first. So what's the pattern here for that power and the index? Here's the index, here's the power. Index, power. Index, power. Right? So it's one less. So that's it. So a sub n is the nth term of a geometric sequence. It's a1 r to the one less in minus 1. So that's called the general term. Let's see if I can do the box again. This rectangle. Okay, did it that time. So that's the general term, or nth term of a geometric sequence. So it's called the common ratio because if you divide the next term from the previous, you get the same thing each time. All right, so let's look at an example. So find a sub n of the geometric sequence. So find a sub n of the geometric sequence. Okay, so the sequence, so it tells you that it's geometric. So you can use everything you know about geometric, which is basically everything just right above, not much else. It's given to be 2, 3, 9 halves, 27 fourths. Okay, so there's my sequence. We know that our first term is 2 because it's the first term. Okay, so the first, second, third, fourth. And so the common ratio, because we know it's geometric, it's true for any two successive terms. We might as well just divide this one and this one. So you can see there that r, so r is, write this down, you're going to need r. So R is always A sub n plus 1 over A sub n. So it's the next. Sometimes is how I think of it, I guess. Next over previous. It's not really the previous because you have to be at something, but anyway. It's A sub n plus 1 over A sub n. That's really how it's defined. So so R is 3/2. Okay, so then A sub n is the first term, and then it's 3/2 raised to the n minus 1. Okay, so there's your nth term. Okay, so try this one. Next example. So 1/2, so same question, find the nth term, etc. So 1/2, 1/4, 1/8, 1/15th? No, 16th? Has to be 16. Okay, etc. Try that one. Pause it, give you a moment. All right, so R, you can see, is just 1/4 divided by 1/2, which is 1/4 times 2 over 1, so that's just 1/2. So R is 1/2. First term is 1/2. Okay, so that tells you kind of a lot. So A sub n is 1/2 times 1/2, because that's R, raised to the n minus 1. But you have 1/2 is to the first power, so it's like this. This is to the first, so you add those exponents, and so you get 1/2 to the n. So it's kind of like something like this. If you had like 3 times 3 to the n, that's 3 to the n plus 1. You add that exponent. So we're doing basically 1 plus n minus 1, which is just n. That's what we ended up doing there. So it's just A sub n is 1/2 to the n. Okay, let's do another example. This is not just given a simple sequence like that. All right, so find A sub 1 and R for the geometric sequence A sub n all right, so A2 is given to be 21. A7 is 5,103. All right, so this is similar to setting up a system of equations, but it's going to be non-linear, which you'll see in a second here. So this means n is equal to 2. This means n is equal to 7. And so A sub 2 is going to be A1, and then it's R raised to the 2 minus 1. So that's just going to be A1 and then times R. But A sub 2 is 21, so you can put 21 there. Okay, then similarly above, you have A7 is equal to A1 R to the 7 minus 1. But A7 is 5,103. and then that's A1R to the 6th. All right, so then you basically have these two equations. You have this equation and you have this equation to solve. So because it actually is somewhat nice numbers, you can solve this for A1 or R and substitute into here. So the simplest thing it looks like to me is solve for A1 and then plug it into there, substitute it in. I think that's the best bet. So we get that A1 is 21 over R, and then we're going to take that and substitute, and you'll see that that R is going to reduce that power. So let's just highlight that so it's a little easier to see. So we're going to take that and put it right here. And so 5,000, and the numbers you'll see will work out. 5,103 equal to 21 over R. They won't always, of course, but it's not so much the nitty-gritty numbers I want you to worry about. So you reduce that. So that'll simplify. So this and this simplifies, makes that a 5. Subtracting exponents. And so you get 5,103 equal to 21R to the 5th. So that's equivalent to saying 5,103 over 21 is equal to R to the 5th. And if you do that division, you get, what do you get? You get 243 is equal to R to the 5th. And so, if you were to solve, so what's the 5th root? So if you do a root, 5th root on both sides, it actually is a 5th root. That's why it works out so nice. So R is equal to 3. So you do the 5th root, right? You do 5th root like this on both sides, see what happens. Okay, I'm going to leave that off. So R is equal to 3. Now back substitute. To find what? To find A1. Okay, so to find A1. So A1 is equal to 21 over 3. So that's 7. Okay, so that implies that A sub n, our nth term of the sequence, is 7 times 3 to the n minus 1. And then we could use that to find something if we wanted to. Often in these types of questions, it'll be like, okay, then use it to find, etc. So this is the one you want to start to. This is a good type of example. Solving nonlinear systems as well. It's an application of that. All right, so now next we will get into the sum of a geometric sequence in another video.